Good morning. This lecture is about submodular polyhedra. So what we're going to be doing is we will define what is a submodular function, and then we will define an associated polyhedron and we will show that it's not only an integral polyhedron, but it's also defined by a TDI system. Good, so then let's start with the definition of submodularity. So it's a very simple definition. We have a ground set capital that we're gonna call always capital N, and it's a set of indices from 1 to little n. And we have a set function, so it's just a function that takes any subset of capital N and associates to it a real number. And this function is called submodular if this inequality below holds for every two subsets of capital N. So what do we have here? We have that the two subsets are capital S and capital T, and we have that the function evaluated in S plus T is larger or equal to the function evaluated on the intersection plus the function evaluated on the union. Good, so let's immediately see an example so that we understand a little bit better what it means to be submodular. And this example is about the cut function. So here we have a graph, as always is denoted as G equal VE, and our function is defined on the nodes. So essentially for every subset S of nodes we have a specific f of s, and in this case in the cut function is defined as exactly the cardinality of delta of s. So remember, delta of s is exactly the set of edges in the graph that have exactly one and in the set capital S. And now you can just check that the cut function is indeed submodular. So what do we have to do? Well, we have to check again this inequality. I just copied it from the previous slide for every S and T contained in this case in V. Good, so we have to evaluate this delta of S, delta of T, the cardinality of these sets, of course, and then delta of S intersected T and delta of S union T. So, and we can see immediately in these pictures essentially that this inequality holds. So let's see. Let's start with delta of S. We have to look therefore at all the edges that have exactly one end in S. Now S is in the picture the set which is red, and T is the set that is blue. So in general, S and T may intersect, and so this is the most general case where they do intersect, but none is contained in the other. So then you see T breaks down the set S into two parts, this and this, and also the outside of S, or the complementary of S, into two parts, this and the rest of the graph, of the nodes. Good, so we have two cases inside S, two cases outside, so we have in total 4 types of edges in delta of S. So there are the ones that have an end in S that is contained also in T, and are this guy, this type of edges that start from S intersected T and end in T minus S. Then there are the edges that, so I'm looking at this type of edges, these are the ones that have one end in S intersected T and the other one in V minus S minus T. And then again you can do the same distinction for the nodes that have one end in S minus T now, so there are those with the other end in V minus S minus T, and then the other end in T minus S. So these are, it's just a way to see to see all the types of edges that are in delta of S. Now to look at delta of T, of course this is just symmetric, so this type of edges become this type of edges. This is the same by symmetry, same for this guy, it's the same as this, and this one of course is this one. So by symmetry it's easy to construct this second set delta of T. What about delta of S intersected T? Well, we must have one end in here in the intersection of S and T, and the other end can be in S minus T, in T minus S, or outside of all of them. Good, so it's perfect. The last case we have to look at is delta of S union T. Here the edges can have one end in S intersected T, S minus T, or T minus S, and then they must just go outside. Good, so now on the left we have delta of S and delta of T. Remember, we have to look at the sum of these cardinalities. And so in particular we will have these edges, I mean the cardinality of these edges, the cardinality of these edges plus the cardinality of these edges plus these ones, and so on and so forth. So now if we sum all of these guys, you see that this is counted twice because it appears both here and here. Then we have this is also counted twice, it's here and here. And then the other appears just here and not in that of T. This one doesn't appear in that of T, and same for this and this. Good, so what about the right hand of the inequality? We have the cardinality of delta S intersected T plus the cardinality of delta S union T. So we're summing all these type of edges that we saw here. Also here you see this guy appears here and here, so it appears again with the coefficient 2. All the edges are counted twice. And then again I'm counting these ones, and these ones, and these ones. So essentially, if you now consider the sum, you see that the sum is almost the same of left and right. The only difference is that on the left I have these edges here with a coefficient 2 that don't appear at all in the on the right, and everything else is exactly the same. For example, look, this one is counted twice here, and it's counted twice here, and these horizontal edges are counted once on the left and once on the right as well. So then this inequality holds because of this nice easy diagram that we just understood. So we checked that the cut function is submodular. Good, so what else can I tell you about submodular functions before getting to the main result that we're going to see? Well, there are some nice links with a bunch of concepts that we're not really gonna be discussing more in the course. So the first interesting link for those of you that took convex optimization or that are interested in the topic is that submodular function can essentially be seen as the analogous of convex function in the discrete case. So that's why that's in a sense this is a kind of a deep connection that we're not again going to discuss, but this justifies in a way why we're going to be able to write down a perfect formulation for the associated polytope that we're going to see next. Also, there are many interesting links with other concepts that if you're interested you can go and have a look at. So in particular, submodular functions have strong connections with matroids and the corresponding polymatroids. They are also connected with the greedy algorithm because essentially the greedy algorithm is able to find an optimal solution for submodular functions and matroid and polymatroids, and there are very deep connections. We're just going to scratch the surface here. Also, submodular functions are linked to connectivity problems on graphs, and we will see just in one slide that, for example, this links nicely with the minimum spanning tree. Also, submodular functions have connections with game theory, and in particular with cooperative games, if you're interested in game theory. Good. So finally, let's define the submodular polyhedron. So we need to have a submodular function, and then we define the corresponding submodular polyhedron, which is defined as follows. The set of points in Rn, n is the same cardinality of the ground set, where all these inequalities hold. So again, for every subset S of n, we look at the sum of all the xj's with j in S, and this must be less than or equal to f of S. So this is just a polyhedron, of course, it's just a definition at this point. And I'm just going to give you an exercise here to understand how it links back with the spanning tree polytope, or at least yeah, okay, so I don't want to tell you too much. This I think is a very interesting exercise. So look at a graph as always, G equal VE, and take N, so the set capital N that we look at in submodular functions, and this has to be the set of edges. And you define f of s, so for every subset S of E, as the cardinality of the largest forest contained in S. And forest is, so we didn't really define forest so far, but we nevertheless look at this concept. So forest is defined as a set of edges that contain no cycle. So very similar to tree, but it doesn't have to be connected necessarily. So the first thing you should do is check that f of s as defined is submodular indeed, construct the associated submodular polyhedron, and then try to understand the connection with the spanning tree polytope. In particular, try to think about faces of the polyhedron that you obtain, and before that even try to understand what are the redundant inequalities. Once you have done these two things, it will be fairly clear what this connection is. This is a very interesting exercise for you. Good. Anyway, let me get to the main, actually the only result we're going to prove for submodular polyhedra. So here's the theorem. We have again our ground set capital N. We have our submodular function f. And what's important here that we didn't assume earlier any times is that f is integer valued. So you see the codomain is not R but is Z. Also, we're going to assume that the function f evaluated in the empty set is 0. This is kind of a technical assumption, but we definitely need it. So then the submodular polyhedron is integral, and not only that, the corresponding system, the one defining the submodular polyhedron, is also TDI. Good, so then let's prove this result. Let's prove this result. And so I just gave you an interesting connection with the spanning tree polytope, and you will see how actually this proof has some common elements with the proof of the integrality of the spanning tree polytope. And of course, that's no coincidence, but it's due to the link that we just discussed. Good, so let's see what we want to do. So just a setup, we show that both the maximization problem, so max Cx such that sum of xj over j in S, so I'm just writing the submodular polyhedron less than or equal to f of S for every S subset of n. So this problem and its dual have integral optimal solutions for every C that is integral, and also for which the max is finite. Note that, so first, when is this max finite? The max is finite if and only if C is greater than or equal to 0. Why is that? Well, of course, if you have a component of C that is negative, then immediately, since you always have inequalities of the form less than or equal to, where, well, you can always let the corresponding xj go to minus infinity, and you obtain better and better solutions, so solutions that goes to plus infinity. Good. So without loss of generality, we can order our elements in the ground set so that the costs are decreasing. This is just for notational simplicity, really. So let me write it. We may assume C1 greater than or equal to C2, and so on and so forth, until Cn, and also greater than or equal to 0. Good. And of course, we have greater than or equal to 0 because we're just assuming that, as we just discussed. Great, now we define some specific subsets of our ground sets that will be important to define the optimal solution of the primal. So let S0 be the empty set and Sj be defined as 1 until j. So very simple, all the elements until j, so for j and n. And this essentially allows us to immediately define our optimal solution. So let x bar j be defined as f of sj minus f of sj minus 1 for every j in n. Good, so the first thing that we should observe is that x bar is integral. So why is that? Because f is integer valued by assumption. Integer valued implies x bar integral. What do we claim? That x bar is an optimal solution. So let me write it. We claim okay, so before showing that x bar is optimal, we need to show it actually is feasible. So we need to show that x bar is in P. So let's do that first. We show x bar in P. So we need to show I'm gonna write it in this form, otherwise, so for ease of notation. So let me explain what I mean with x bar of t. So this for every t in a subset of n. So these are supposed to be the inequalities in our polytope, right? Therefore, here we use the notation x of t equal to the sum for j in t of xj. Okay, so how do we prove this inequality? The proof is by induction. On the cardinality of t. And the base case is trivial, of course. So the base case T is the empty set being trivial. Okay, so why is this trivial? It's because, well, x bar of the empty set on the left hand of the inequality you have to show is clearly 0 because we're summing no terms. And the right hand is f of the empty set, which is 0 as well. So that's why the base case is trivial. Good. So at this point, what do we do? Essentially, this proof by induction relies on picking the very last element in our set capital T. Let's call it K and then see how we can use it. So let K be defined as the max J in T. So note that T is contained in Sk. Remember, Sk contains all the elements from 1 to k, and since k is the largest one in T, of course, this containment holds. So also, we're going to use induction on the set T minus k. Of course, this is smaller than T, and so we can use induction. And so this is less than or equal than f of T minus k. Good. So then, therefore, we have x bar of t. That's what our left hand of the inequality we want to show. So now we break it down into x bar of t minus k, and of course plus x bar of k. Now we immediately use induction, so this is less than or equal to f of t minus k plus x bar k, and this is induction. I'll just write it here. Now I just use the definition of x bar k. So again, we have f of t minus k, just copying, plus, here's the definition, f of sk minus f of sk minus 1. Good. And so this, let me just write it, definition of x bar k. And at this point, I claim that this is less than or equal to f of capital T, which is of course exactly what we want to show. It's just a little bit unclear at this point why this is true. And this just follows from the submodularity of f. So essentially, now I'm going to write it, but we're going to use as the two sets in the definition of submodularity, we're going to use T here and sk minus 1. So now if you bring this f of sk minus 1 down here, you see that this inequality is exactly should hold by submodularity if, so why? Because we're going to show that the intersection of these two yellow sets, T and sk minus 1, is exactly T minus k, and the union is exactly sk. So let me just write it so that it's a little bit clearer. So where the last inequality holds, since f is submodular, since so T intersected sk minus 1. Remember, the largest element of T is k, therefore T intersected sk minus 1 is exactly T minus k. And what about T union sk minus 1? Well, T, remember, the largest element again of T is k, so union sk minus 1, we obtain exactly sk. Perfect, so that's exactly what we wanted. The intersection is T minus k and the union is sk, so the inequality above holds as we claimed. Okay, now we have to talk about the dual. So we're done with the feasibility of x bar. That's what we've shown so far. And so to conclude the proof, we just need to give an integral feasible solution to the dual with the same objective as x bar, as the primal x bar. Because then we will have that the dual solution is optimal and integral. Good. So essentially, the whole reason we obtained, I mean, there are several ways to prove this theorem, and essentially to prove it, we just need to show that the system is TDI, right? So really, we just needed to construct an integral optimal dual solution for every integral C, blah, and so on and so forth. Here we constructed also the primal solution, essentially because then in the dual we can only show feasibility and use strong duality. So let me write then what is next, what we want to do. So to conclude the proof, we only need to give an integral feasible solution for the dual whose objective value equals Cx bar. So what is the dual then? The dual is min sum of f of s y s for every subset s of n, subject to sum of the ys for j in s equal to cj, yeah, for every j in n, and then non-negativity ys greater than or equal to 0 for every s subset or equal to n. Good, and here you will start to see even more similarities with the proof of the spanning tree polytope. So we need to define now the dual solution that we claim is optimal. So here it is. We define a dual solution at y bar as follows. So y bar s defined as cj minus cj plus 1 for every s among the sj's. So for j equal 1 until not the last but next to last, and then cn for s equal n. So very similar to the definition in the spanning tree case, 0 otherwise. Okay, so once again, as we did for the primal, the first thing to observe is that C integral implies y bar integral. Then we need to check dual feasibility, which is immediate to verify. So I don't assume that's a good exercise. It really just takes a second. So please do it. It is immediate to verify that y bar is dual feasible. So what we need to check is then the objective function value. So furthermore, we have, do we have enough space here? Yeah, I think so. So let me write it here. So sum, that's the objective function of the dual f of s y bar s over every subset s of n. So this is equal to, so let me just use the definition of y bar. So this is f of sj times cj minus cj plus 1. So these are all the terms corresponding to the definition. This guy is right. Then what about this definition? Let's add it here, plus f of n times cn, and everything is a 0, of course, from the definition of y bar s. So now we write the same sum as, by looking separately at the different cj's. So again, sum for j equal 1 until n now of cj times, so for every j we will have f of sj with a plus sign minus f of sj minus 1 with a minus sign. So this last sum is just another way of writing the previous sum, of course, by just focusing on the cj's. However, there's just one key difference. In this last sum, we have consider j equal to 1. We have c1 times f of s1 minus f of s0. And as you can see, f of S0 never appears in the previous sum, but that's no problem. The two sums still are the same because we know that f of the empty set is equal to 0. Good. So at this point, we're done because this parenthesis is exactly x bar j by definition of x bar. So the two objective function values of y bar and x bar coincide, and so x bar is optimal for the primal and y bar is optimal for the dual. So let me write it. Therefore, x bar is optimal for the primal and y bar is optimal for the dual. And that's everything we needed to show. Perfect. Great, so then let's get back to our slides. That's our theorem, proven, great. What we can observe from this proof, exactly in the same way as we observed for the spanning tree polytope, is that the proof not only proves the TDI-ness and integrality of the polytope, but it also gives an algorithm to compute the optimum of the primal. So what you have to do is essentially follow the steps of the proof. So order the elements in the ground sets so that the cost is decreasing. Define the sets as in the proof. So you have S0 is the empty set, and Sj equal all the elements in the ground sets from 1 to j for every j. And at this point, an optimal solution x bar is defined as in the proof. So x bar j is f of sj minus f of sj minus 1. So as you can see, this is exactly the same thing that happened for the spanning tree polytope. And again, this algorithm is known as the greedy algorithm. And that's everything we're going to see about submodular polyhedra.